Hi there, folks. Today we're looking at rules of exponents involving square roots. And really, this comes down to one thing that maybe you don't know about square roots, and it's that little 2 that we can't see but we know is there. So when we write a square root, we just write it like this. But really what that means is this. It's like a little 2 in that kind of crevice between the two lines, all right? And we don't write the 2. That's just because mathematicians at some point decided, you know what, we use this a lot. Everyone will know that there's a 2 there, all right, until everyone forgets that there's a 2 there, right? So please understand that there's a 2 there. And keep in mind that when you get to higher level mathematics, if you are working your way towards that, we have other roots, like the cube root is written with a little 3 in there, or the fourth root is written with a little 4 in there, all right? Again, for our purposes, we're only going to look at square roots, but it's important today to understand that even though it's not written there, there is a little 2 there, okay? So keep that in mind. So now let's see if we can discover this rule for exponents. If we look at something like this guy, let's approach it from that factor tree method, okay? If I were to do a factor tree here, x squared is x times x, right? So that's what my factor tree would look like. And remember, when I do my factor tree, I look for pairs. Here's a pair of x's, so I put an x on the outside. But there's nothing left by itself. Remember, the thing that's by itself goes under the square root. Since nothing's by itself, I basically don't have anything under the square root. It's just this, okay? So that's my answer this time, okay? If I look at the next one, again, factor tree. If I were to do the factor tree, and I'm not going to do it like I would traditionally do the factor tree, I'm just going to break it up. This is y times y times y times y. It's 6 y's, right? Isn't that what y to the 6th power means? So now I'm going to circle pairs. Here's a pair of y's, so I put a y on the outside. Here's another pair of y's, so I put a y on the outside. And here's one more pair of y's, so I put another y on the outside. There's nothing left by itself, so I don't have anything left under the radical, but y times y times y, that's y to the 3rd power. If I look at the next one, again, not my traditional factor tree, but I know b to the 10th power, that's like I have 10 of these things. Whew. And once again, when I do this, I'm going to look for pairs. So here's a pair, so I put a b on the outside. Here's another pair, so I put another b on the outside. Here's another pair, so I put another b. I just keep doing this till I run out of pairs. There's another pair, so another b. And looks like there's one more pair, so I put one more b. And notice there's nothing left by itself, so there's nothing left under the square root. But now b being multiplied 5 times, that's the same thing as b to the 5th. And hopefully, just like our other rules of exponents, you're looking at this going, wait a minute, Mr. Jansen, I see a shortcut here. The shortcut is I divide the exponent by 2. And the reason for that is because there's a little 2 here. I know it's not written, but there's a little 2 here. That's what I'm dividing by. So here I do 2 divided by 2, and notice x to the 1st. 6 divided by 2, y to the 3rd. 10 divided by 2 is b to the 5th. All right, so this falls right in line with our other rules of exponents. I divide the exponents this time, okay? And it just so happens I divide, when I take the square root, I divide the exponent by 2. Now, keep in mind, this rule is a little bit more generic than that. Sorry, I scrolled back up to show you this. But right here, if you had the cube root, guess what you would divide each exponent by? 3. If you had the 4th root, if there's a little 4 in there, you would divide each exponent by 4. If there was a little 5 there, you would divide each exponent by 5, okay? For our purposes, we're only going to look at square roots, so we're only going to divide by 2, all right? For example, if I look at something like this guy, here I have the square root of x to the 12th. I know that there is a little 2 right here, so I'm going to divide the exponent by 2. That's going to be x to the 6th power. If I look at the next guy, I know there's a little 2 here, so I'm going to divide the exponent by 2. So this is going to be y to the 21st power. This one, I know there's a little 2 here, so I'm going to divide the exponents by 2. 16 divided by 2 is going to be x to the 8th. 4 divided by 2 is going to be y to the second. And again, this only applies to exponents, all right? So if we had a number under there in front of that x, I would have to take the square root of that the same way I did in the previous lesson, where I'd either have to do my factor tree or look for perfect squares, okay? And we'll see some of those a little bit later, all right? But we just divide the exponent by 2. Now, hopefully you realize where this might be problematic. What if the exponent isn't divisible by 2? Ready? What in the world am I going to do if it's not divisible by 2? How can we take the square root? Well, it's kind of like when we did the factor tree, we only took the pairs out and anything that didn't have a pair got left behind, all right? We left it underneath that square root. Well, we kind of do the same thing, and we've done a version of division where we talk about like the division versus what's left over. All right, so we kind of think of it in the leftovers. It was called the remainder. All right, and if we think of this in terms of the remainder, watch this. So if I put the little 2 here, think about 5 divided by 2. See, when you first learned division, you would say, well, 5 divided by a 2 is 2, like 2 goes into 5 twice, but not evenly. There's some left over. There's actually 1 left over. And what that's telling us is telling us the exponent on the outside and the exponent on the inside. In other words, 5 divided by 2 is 2, so it's x to the second. But there's a remainder of 1. In other words, there's 1x left over under the radical. Okay? And so again, think about it in terms of division. Watch this. If I take it off to the side, 2 goes into 5 twice. And then 2 times 2 is 4. Remember doing long division like this? Oh, there's a remainder of 1. So it's 2 with a remainder of 1. Here's the 2. Here's the 1. Right here's the 2. And right here's the 1. We didn't write it. Okay? So we just want to think of this in terms of dividing and then what's left over after we divide. Okay? Same thing with the next guy. If I look at this, so I know there's a little 2 here, so ask yourself, 17 divided by 2. How many times does 2 go into 17? The answer is 8, so it's a y to the 8th out here. But now how many y's are left over? Okay, so again, go back to think about division this way and say, okay, 2 goes into 17 8 times with 1 left over. So I put a y to the first under here. Okay, if I look at the next one, x to the 8th, well, I can divide that one by 2. Ready? 8 divided by 2 is a 4, so it's x to the 4th. But then the 3, 2 goes into 3 once, so a y to the first, but with a remainder of 1, so there's 1 left over. So it's a y to the first underneath. So we just want to think about that division the first way we ever learned division. How many times does that go in there? And then how many are left over? So now let's throw some numbers back in there, okay? And really all we're going to do is we're going to do these separately. Remember, when we're taking the square root of a bunch of stuff, I can take the square root of each thing by itself. In other words, for this one, I could take the square root of 8 and then separately do the square root of the variables. All right, and that's essentially the way I'm going to approach it. See, the square root of 8, whether you do the factor tree or whether you look for perfect squares, you're going to do that the way we already learned it. And then you're going to do the variables separately using our rules of exponents, dividing them by 2. Okay, so over here, I'm going to do the perfect square method. If you're really enjoying that factor tree, please keep doing the factor tree. Okay, don't let me stop you. 8 is 4 times 2. The square root of 4 is a 2, so I put a 2 on the outside. But then I can't take the square root of this other 2, so it stays like this. Okay? Over here, I divide each of these by 2, so I'm dividing the exponent by 2. So 6 divided by 2 is a 3. And then 5 divided by 2 is 2 with 1 left over. Okay? So now if I kind of recombine these, just look at the stuff that's outside the radical. I've got a 2, an x to the third, a y to the second, and then underneath I have a 2 and a y. And I'm done. So split them up. Do the numbers the same way we've always done numbers, okay? And just like our other rules of exponents, they only apply to exponents. Numbers still do the same thing numbers have always done, so treat them separately, okay? Same thing with this guy, ready? Let me split it up here. I'll put the 72 over here, and then I'll do the variables over here. So the 72, you either do your factor tree or look for perfect squares. I'm going to do the perfect squares. So that's 36 times 2. And now I just take the square root of each of these individually. The square root of 36 gives me a 6. The square root of 2 just gives me the square root of 2. And now over here, remember, I'm dividing the exponents by 2. 7 divided by 2 is a 3 with 1 left over. 10 divided by 2 is a 5, and that divided evenly, so I'm done. Okay? But now combine these back into one square root. Ready? There's a 6 on the outside, an x to the third, a y to the fifth, and then inside there was a 2 and an x. Okay? So I'm just putting all this stuff that was on the outside, and all the stuff underneath here goes underneath. Okay? And that's it. We just deal with these two things separately. We use our rules of exponents for the variables, and we simplify the numbers the way we already have learned how to simplify them. Okay? If I look at these guys. So again, split it up. Ready? It's the square root of 12. Over here, I'll do the square root of x to the 9th, y to the 11th. And so the square root of 12, I'm looking for those perfect squares. That's 4 times 3. And now I take the square root of each of those things. The square root of 4 gives me a 2. The square root of 3 is the square root of 3. Okay, it can't be simplified. Over here, there's a little 2, so I'm dividing the exponents by 2. 9 divided by 2 is a 4 with 1 left over. And actually, I should write that a little bit lower so I can see what's going on, right? Sorry. Let me write this a little bit lower. So it was here. So it was a 4 with 1 left over. 11 divided by 2 is 5 with 1 left over. Okay? And now just combine them back into one square root problem. So I've got a 2 on the outside, an x to the 4th, y to the 5th. Underneath I have the 3, an x, and a y. And that's it. Okay, so I'm just dealing with the numbers separately from the variables. Ready? Same thing here. Ready? This is a 3 and then the square root of 50. See, I've sectioned off those numbers. That's the same thing we've been doing. And then here's the variables. So the numbers, I'm looking for perfect squares. That's 25 times 2. Here I can take the square root of 25. The square root of 25 is a 5. And notice I already had a 3 on the outside. So now I also have a 5 on the outside. The square root of 25 is a 5. The square root of 2 is just the square root of 2. So now this becomes 15 square root of 2. For the variables, I divide by 2. Remember, there's a little 2 here. My rules of exponents, I divide the exponents by 2. But watch out for that x. That x, when I don't see an exponent, that's a 1. And really, can I do 1 divided by 2? It's really the only thing I can't even start the division on. So I can't do that one at all. The x is just going to stay underneath the square root. Okay, there's nothing I can do there, all right? 15 divided by 2, well, that's a 7 with 1 left over. And now I can rewrite these as one square root function. Sorry, these are running into each other. So on the outside, I have a 15. I have a y to the 7th. On the inside, I have a 2, an x, and a y. Okay, so when I'm taking the square root of variables, I'm just dividing the exponents by 2. That's my rule for exponents. So numbers, we split them up. So do numbers the same way we've always done numbers, but for the variables, we divide the exponents by 2. Okay?